Okay, it's time to do day 8. I am getting way behind. Look at that. Current one is day 14, about to be 15, so I better get my skates on. All right, let's start off looking at 8. Roof of a top secret Easter Bunny installation. Of course we are. Oh dear, we have an evil antenna that makes people buy Easter Bunny band imitation mediocre chocolate. There are actually many such antennas. Each antenna is tuned to a specific frequency by letter or digit. So there we have a map that has, I guess it's got 4 0 antennas and 3 A antennas. The signal only applies this nefarious effect at specific antinodes based on blah, 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 blah. Any point that is perfectly in line with 2 antennas of the same frequency, but only when one of the antennas is twice as far away as the other. Oh, okay, so from the node. All right, so let's look at the example here. These 2 antennas with frequency A, they create 2 antinodes marked with a hash. All right, so there's the line. Ish. Let's try that again. So there's the line, and this guy is 1 across and 2 up. This guy is 2 across and 1, 2, 3, 4 up. Okay, so this one is twice as far from here as there, and then that one's symmetrically the opposite way. Okay, we can deal with that. Adding a third antenna creates several more antinodes. You would ideally add 4, but 2 are off the right side of the screen. Okay, so let's draw our lines again and see if we understand what's going on here. So there's one of our lines with 2 nodes. Here's a line, and then there's a node off the screen here. And then here's our last line, and there's a node off the screen there. Okay. Antennas with different frequencies don't create antinodes. A and A count as different frequencies, can occur in locations that contain antenna. Okay, so A has this uppercase A here doesn't really count, it's not useful, but if we draw our lines again, then it's at the place where there will be a node from those 2 A's. Okay, so does what our results should look like from running this. How many unique locations within the map contain an antinode? What we have to do is to get a map like this, somehow represented in our code, look for groups of antenna that have the same character, and then for each of those groups, we have to work out the line that joins them, and then extend it and find places on that line where it's one distance away from one of the antenna and twice the distance to the other antenna. But looking at this, if we take, say, this guy, the nodes can only occur on the grid points. So the antenna are on grid points and the nodes are also on grid points. Okay, so that's just a constraint, and that's why there aren't like an infinite number of antenna. Okay, so let's go and start coding. So mkdir 08 cd08, clear the screen, and n08.rb, 08.rb. Cool, all right, so let's get that data loaded in. So we'll pop back over to our browser window, copy that data, back over to the code, we got Copilot enabled again. Copilot detach. Okay. So now we have to read this data in somehow. What kind of data structure are we going to use for this? Well, we could just use a 2-dimensional array, but I don't think that's going to help very much because we don't care necessarily about the map. We just care about where things are in the map. Oh, and we've also got the situations where we'll have multiple things at the same place, like an antenna with a node on top of it. So having just a 2-dimensional array is going to be a bit of a pain. So let's just store the location of each of the antenna as an XY pair. And we had to group it by different frequencies, so we'll have a separate list for each of those different letters. Okay, we can do that. So def load data from some file, file.each.with index, because that's going to give us the y coordinate. And this is y, yeah. So the first thing we do with that line is line equals line.chop. We're going to remove the new line. And we'll do the same as we did last time, because that was really quite useful. If the line is empty, we'll break. Okay, in fact, we'll do that in one line just because it's a little bit tidier. Okay, otherwise the line's not empty, so we have to iterate through the characters in that line. So it's going to be line.eachchar, and this is in the x direction, so we still need to have a with index do ch, comma x. There we go. Okay, so now we have our coordinates x and y. If this character represents an antenna, we need to remember it. And an antenna has a frequency. The character is the frequency, so it has to be represented as A to Z, 0 to 9, close thingy. So at this point, we actually need to store our XY pair, and we don't have anywhere to store it. Okay, so you need to create somewhere to store it. Is that going to be a list? No, because we're going to have separate ones for each frequency. So we're going to have a hash. So we're going to have, let's call it freaks. It's an empty hash. So down here, the ch is the frequency. Let's rename that because it's a bad name, ch. Boom. Okay, so we're going to index into freaks with our frequency. If it's not there, if there's no current entry, we're going to create an empty list, and then we're going to append to the entry that's there our XY coordinates. Okay, and then we'll say end for that. And one extra end, just for good luck. And I guess we can try running it. Oh, it's returning the file object. Why is that? Oh, because we're not returning freaks from the top there. Oh, okay. So there we have 1, 2, 3, 4 O's and 3 A's. Cool. All right, ship it. So what do we have to do now? So we have to go through this and find the lines. And to find the lines, we're going to need the slope. So let's go through this again. For each frequency, we're going to go through all of its antenna, and we're going to look for all the lines that can be drawn between each antenna. Then we're going to match that up with our grid, and we're going to find the points on the grid on that line, which are 1 and 2 times away from the 2 different antenna. But we only want points on the grid on the line. So let me just do a quick bit of sketching here to see if this helps. If we have a grid, and we have here and here, let's say here and here. Let's make this grid just a little bit bigger. So if we have a point there, okay, so we got a point here, and a point here. Then the line, it goes through here, 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 and then over here. Okay, so how are we going to find points that are on the grid and on the line? Time for a quick, really bad diagram, I think. Oops, wrong thing. So if this is our grid, we're in rainbow color mode. Isn't that pretty? And then we got our lines going down. Okay, so let's imagine we have a point, an antenna here, and an antenna here. So that is 2 across and 1 down. Okay, our grid is not accurate, but every point on the grid that passes through those two is going to be on that same slope, right? So 1 down, 2 across. So we know then that if we take the slope, if we use the actual numbers from the slope, that will tell us where each grid point is. Okay, we've loaded our data in. So for each of our frequencies, so that's going to give us the actual frequency and the list of antenna. And what we want to do is we're going to basically find all of the nodes for that frequency. So let's write lots of functions here just because it's easier to keep track of what's going on. So we'll look for all of the nodes for that frequency. And that's obviously going to take in the list of antenna. And it's going to need the map. Okay. What are we going to do with that? Well, we need to remember the nodes, don't we? And all we care about, I think, on the instructions were the occupied nodes. So we can just use a set for this. So if we have nodes equals set.new, and then down here we want to say nodes plus equals nodes for frequency. So if nodes for frequency also returns a set, then the plus equals is going to do a set union. So this will just accumulate all the nodes for everything. Okay, so let's write nodes for frequency. And what do we take? We take an antenna, antennas plural, and we take the frequencies. Okay, so we know we're going to be returning a set, so let's just set that up now. And at the end, return nodes. So we need to look at every possible unordered combination of antenna. Okay, and to do that, you just basically go through the list one at a time, and for each element, you look at all the subsequent elements, or you pair it with each of the subsequent elements, and that will give you every combination. Okay. Yeah, okay, so let's do it this way. We'll mutate antennas equals antennas.dupe, so we're not going to corrupt the original one. And then we're going to go through that list, so while not antennas.empty, So we're going to take our initial antenna, antennas.shift. We're shifting, that means we're going to reduce it by 1 each time, so our loop will terminate. That has given us 1 point, and now antennas is all the rest. Yeah, so we've taken the head of the list into initial. And the tail of the list is all the rest of the antennas to look at. Now for each of those additional antennas, it's going to be antennas.each do antenna. Why couldn't I just call it A? So we've worked out we need to know the slope. So let's assume we have something that's going to tell us the slope. Initial and antenna. And then we're going to iterate all the different points on that slope. So, again, let's just defer that to sometime later. Iterate slope. And what's that going to need? It's going to need the, well, all it can have is the initial point and the slope. And I'm not too sure what we're going to do in there. All right. So let's go up to slope between, because that's the easy one. Actually, it's going to be P1 and P2, isn't it? So let's just call it X1, Y1, X2, Y2. So dx equals x1 minus x2. Order doesn't matter as long as it's consistent. dy equals y1 minus y2. And the slope is going to be, well, just dx dy. Is that true? No, it's not true, is it? Okay. So imagine we have a grid, many lines. Okay. And we have a point. So we have a point here and a point down here, yeah? And then so we have a line that goes between those 2 points. Now, the dx and the dy are both pretty large numbers. But this point here, I haven't counted, so I'm just guessing, might be twice as far from here as here. So we actually need to find the smallest numbers, the smallest jumps we can make to be on that line. So if this guy's got like a dx of 7 or 8 or whatever it is, and a dy of the same, we actually want to make it so that it's, 1, 1 or 2, 1 or whatever the what is it going to be? It's going to be the greatest common divisor. Yeah, it's going to be the greatest common divisor, isn't it? So if it's like 8 and, no, it's a bad example, 6 and 4, then what we want to do is divide both by 2 to take it down to 3 and 2. Yeah, so if we do scale equals dx.gcd dy, so therefore our slope is going to be that times, no, that divided by scale, and this divided by scale. Okay, getting there. So now we want to write this iterate slope thing, and that takes an initial point and a slope. So let's just call it P1 and a slope. I'm going to return every point on that slope. So all we're going to be doing is we're going to be returning P1 plus slope, and then it's going to be P1 plus 2 times slope, and then 3 times slope, and etc., etc. Now we don't currently have algebra on our slope, so we'll just do this the hard way. So we're going to start with our P1. So let's just call it initial equals P1, and then we'll just loop. So then we're going to have, oh, it's the wrong way around, isn't it? Because what I want to do here is to have my initial point here, and then I'm going to have P1, or just actually let's just call it node equals initial. And then the first thing we're going to do is to add the slope into node. So let's just assume node equals add slope node comma slope yield node. So here's my question. What's going to terminate that? Well, it terminates when it runs off the map, right? But we don't know when we run off the map because we don't actually have a map. All we have is a bit of points. And none of those points tell us necessarily how wide the map is. Because if we go down to here, we can't just use, for example, the largest X or the largest Y, because it's got 2 lines after the largest antenna and also 2 columns after the largest antenna. So we're actually going to have to record the shape of that input as we collect it. And that's up here in load data. So that's going to be something like, we'll set our initial width and height. And we might as well just do the same. Height equals 0. And then the height is whatever the value of y is at the end. So, and remarkably inefficiently, the same is true for the width. Width equals x. So now we've got the size of our data, and now we've got to find a way of returning it. Now previously what we did is, as our freaks is a hash, we just stored the width and the height in that same hash using, distinguished keys. That feels a little bit ugly for this particular, I mean, it felt ugly the last time, but it feels even more ugly for this. So I'm about to do something fairly unusual for me and create a class. In the last, year or two, I have found myself writing classes less and less and less. So this load data thing is now going to be our initialize, our constructor. And these guys are going to be instance variables. At freaks, at width, at height, and we no longer need to return it. And we'll make freaks accessible read-only. So attra reader freaks. Okay, so let's come back down over here. This is going to be freaks. Actually, no, it's not anymore, is it? It's going to be map equals map.new data. And I guess we could just say map.freaks.each. And we'll pass the map in and not the frequencies. Okay, so now in nodes for frequency, we're going to get a map here. And when we iterate here, we're going to have to pass that map in because it's the iterate that needs to know the size. So we'll add a map there. If in doubt, add a new parameter. Okay. So if we have a node and it's outside of the map, we want to stop. We don't have to do anything anymore. So let's have the map determine if the node is inside it. So we'll say something like break unless map dot contains node. So then we have to write a quick contains thing up here. Def contains, and the node is just xy. So that's going to be x is going to be greater than or equal to 0, and x is less than or equal to at width, and y is going to be greater than or equal to 0, and y is going to be less than or equal to at height. Okay, I like little predicate functions like that. So that's going to add the slope in and stop when it goes off the edge of the map. So now we just need a quick add slope. And it receives the node, which is xy, and it returns the, it receives the slope, which is dx dy, and we're just going to return x plus dx, y plus dy. Okay, so in theory now, we should have enough code that we will here return the nodes that are along a line. So if we were just to output that node, we'll just see how many mistakes I've added to this. Expecting an expression after the operator. Greater than or equal to, less than or equal to, at width. Oh, 0. Oh, okay. So we actually did something here. It looks like we're following a line, and then in line 67 we blew up because there's nothing called freaks, and there isn't. It's map.freaks, but we don't care about that anymore. Okay, so we've actually just reported on some nodes. I think the time has come to write a little bit of code to draw our map so we can actually see what's going on. That's not part of the problem, and it's going to take a few minutes. So rather than make this even longer than it will be, I'm going to stop recording and then start recording again when I've got that added. So I'll see you in a few minutes. Okay, I'm back. Here's what I've come up with. It basically just iterates over our virtual map, just the coordinates, and it says, okay, do we have a node at that point? And if so, it's going to output a rather pleasant, that 35 is magenta, reverse video, so it's going to basically turn the background magenta. And then if we have a antenna at that point, we'll output the antenna, otherwise we'll output the dot. So in theory, map.draw, and we pass in a bunch of nodes, should show us what that looks like. So if we here say map.draw nodes, are we actually collecting nodes? No, we're not. Okay, so what we're going to do here is to say nodes.add node, because that's our set that we're building of nodes. So then we're going to return the nodes from there. That's going to add them into the overall nodes, and then we're going to try and draw it. Alrighty, let's see what happens. Oh, undefined method draw for class map. I dispute that. I must have got a I'm going to shrink the font down. I hope you can still read it. Just I want to be able to put more on. BAC equals. Oh, it's an instance of map. That's why. So that should be lowercase map. Hey, look at that. Okay, so here's our little grid. We have our O's, and we're just drawing a line for the ones that are lined up. Oh, but look, we're not doing the whole line. So we're missing points like here and here. And we should have ones, yeah. Oh, you know why? It's because we're only going in one direction here. When we iterate the slope, we're adding in the slope, but we should also subtract the slope to go the other way up the line. Okay, so we don't want to duplicate all that code, so what we need is a loop. So we'll have like -1, 1, dot h do direction. We need to set our node there inside that loop, so we reset back to the beginning. And we need to pass the add slope, the direction into add slope. So back up here and add slope. Here we're going to have direction, and then all we have to do is to multiply the dx and dy times direction. Okay, so now we should have our line going both ways. And we do. Okay, so we're getting there. So now all we have to do is to do that business with the distance, right? So we only want to add the node in if that node meets whatever the distance criteria is. Okay, so let's just code that and see what happens. If distance criteria met, and that's going to have three things, right? It's going to have the 2 points. So it's going to have initial and antenna and node. Then, if that's the case, we will add in that node. And so now we just need to have distance criteria met. So we're going to have 0.1, so it's going to be x1, y1. We're going to have the... Actually, I don't think we even need to worry about that, do we? No, not yet. Initial, well, let's just call it P1. P1, P2, and node. All right. So just because we're having lots of methods, we'll have the next method called deconstruct P1, P2. So we'll have D1 equals distance between P1 and the node, and D2 is the distance between P2 and the node. So let's write distance between x1, y1, x2, y2, and it's going to be good old Pythag, right? So it's going to be dx equals x1 minus x2, dy equals y1 minus y2, and then it's going to be math dot squirt dx times dx plus dy times dy. Cool. Oh, but we don't need the square root either, do we? Because if a distance is twice as much, then the square of the distance is 4 times as much. We don't need the square root. We just have to adjust that and put 4 rather than 2 when we're doing our multiplication down below. So let's make this call, let's call this distance between squared So now, if the distance from, if d1 equals, now it's going to be 4 times d2, or d2 equals 4 times d1, then the distance criteria are met. Yeah? So in theory, I think we're pretty close to done. Let's see what happens. Oh dear. We cannot spell to save our lives. Distance criteria. Oh, okay. So if we look at the picture that they gave us down the bottom here, well, I think ours is prettier. It looks pretty much the same. What they want us to do is to count unique locations, though, right? So what we have to do here is to say puts nodes dot, is it size? I can't remember what it is for set. Let's have a look. Yeah, 14. And they have 14 over there. I'm pretty happy with that code. I think it's probably about as good as we're going to get. So let's go for it. So back over to our thing, get the puzzle input. Back over here. Paste the puzzle input. All right. Save that away. 327. I think we should have a look at the map, don't you? Wow. Okay. So let's see if 327 is the correct answer. That's the right answer. Wow. Excellent. You know what? We're getting good at this. Okay, continue to part 2. Oh, obviously we did not take the effects of resonant harmonics into our calculations. Silly us. It turns out that an antinode occurs at any grid position exactly in line with at least 2 antennae. Oh, so every antenna which is paired is going to be a node, and otherwise you don't care about the distance. Okay, so let's go back to our code. And the first thing we can do is just get rid of distance criteria met. because we no longer care about the distance. But is that all we need to do? I don't think it is, because well, let's have a look and see what happens. So let's save that away. Go back to the original example, which is this guy here. P A. So we're looking for something with 34 antinodes now that looks like that picture. So save that away, run it. 33. Of course it's going to be 33 and not 34. The original example now has 34 antinodes, including the antinodes that appear on every antenna. Oh, and look at this. Here we have a 0 antenna that is not marked as an antinode. So, why is that? Oh, okay. Yeah, the problem here is that in iterate slope, we didn't return the first node. We only returned it after we added in. So I think we just need to move that line there to here. So that will now add in the node plus all the rest. If we do Ruby 08.rb 34. Well, that was remarkably simple. I gotta say, these part 2s seem to be getting simpler. I suspect I'm going to regret saying that. So let's go back and do it for our big map now and see what happens. So we can get rid of all that. And stick it down the bottom here instead. Save that away. One, two, three, three. All right, well, let's see what happens. Yay! Excellent. So having a look at our code again. At our interest, we're up to 110 lines for this. I mean, this is relatively verbosely written. There's lots of extra functions and things, but even so, we're getting longer each time. What do we think of the code? I'm actually pretty happy with it. I like the fact that to change the algorithm to the second part was just a question of basically removing one function call and shifting one line up in a loop, which is nice and robust. I think I'm okay with the fact that I didn't have a class representing points. I get away with just passing them around as two-element vectors, and that's fine. Yeah, I think this is actually not too bad. I'm sure there's somebody who's got it done in like 2 lines of APL, but you know what? I had fun. Cool. In that case, we're done, and I will see you for number 9.